There are places in the universe where everything stops. Not stops in the sense of resting or pausing or coming quietly to an end. Stops in a far stranger sense than that. There are places out there, scattered through the darkness between the stars, where the ordinary rules of the world simply give way. Where the path that light travels bends until it closes into a circle. Where time itself, the steady ticking that carries all of us forward together, slows and stretches and finally stands still. Places from which nothing that falls in can ever climb back out. Not a spacecraft, not a stone, not a cry for help, not even a single ray of light, the fastest thing there is. We call them black holes, though the name, when you think about it, is not quite right on either count. They are not really holes in the sense of an absence, an emptiness, a gap in things. They are the opposite of empty. They are the most concentrated, most intensely present objects that exist, so much matter gathered into so small a space that the fabric of reality itself gives way beneath the weight of it. And they are not exactly black either, as we will discover in time, for they turn out to have a faint and marvelous glow of their own that nobody expected, and which we will come to at the very end of this story. But the name has stuck, as good names do, and it captures something true even if it is imperfect. Because what they most resemble, from the outside, from where we stand, is a hole. A place where the universe simply stops, a perfect sphere of absolute darkness hanging in space, out of which nothing ever comes. And the story of how we came to know about them over the last few centuries is one of the strangest and most beautiful stories in all of science. Because unlike almost everything else we have ever discovered, black holes were not stumbled upon in a telescope, not found by looking. They were dreamed up first. They were pulled out of mathematics, long before anyone had the slightest evidence they were real, by people working with pencil and paper, following equations into places so strange that even the ones who found them refused for decades to believe that such things could actually exist. The universe, in the end, turned out to be stranger than they were willing to imagine, and it took 100 years and some of the finest minds our species has produced to accept what the mathematics had been quietly insisting on all along. Tonight, and over the nights that follow, we are going to tell that whole long story, how the idea first appeared centuries ago in the mind of a country clergyman, how it was reborn in far stranger form from the greatest theory of the modern age, how it was resisted, fought over, and dismissed by the most brilliant scientists alive, how it was finally proved in the darkness by the strange behavior of distant stars, and how, only a handful of years ago, we managed at last to do the thing that had seemed forever impossible and take a photograph of one. It is a story about looking into the deepest dark there is, and it is, I think, a wonderfully gentle thing to fall asleep to. But before we begin, let me ask you something softly. If these quiet journeys through the great mysteries of our world help you set down the weight of your day and drift off into rest, then please, take just a moment to subscribe. It is one small tap, but it means the next of these will find its way back to you on some future restless night, and it helps, more than you might imagine, to keep these stories being made, for you and for all the others out there in the dark tonight looking for a little peace. So if you would subscribe and travel on with me, night after night, through the great slow stories of how we came to understand our universe. And I would love to know, from wherever you are resting tonight, in whatever quiet corner of the world happens to hold you, where you are listening from, and what hour it has reached where you are. Leave it in the comments below. It is a lovely thing to see all the places and all the hours gathered there together, all of us drifting off beneath the same turning sky. And now let your shoulders come down, and let your breathing slow, and let the whole weight of your day loosen and fall away. Come with me, out past the roof above you, past the clouds, past the moon and the planets, out into the great quiet dark between the stars, and let us begin very gently at the beginning. Let us begin with a stone thrown into the air. You have done this at some point, most likely as a child. You pick up a stone, and you throw it upward as hard as you can, and it rises, slowing until it stops, hangs for a moment at the top of its arc, and falls back into your hand. It always comes back. That is simply what happens, on this world, when you throw something up. The Earth pulls it back down, but throw it harder, and it goes higher before it returns. Harder still and higher still. And so a question naturally arises, one that people began asking seriously a few centuries ago, once they had a proper understanding of gravity. Is there a speed, some particular speed, at which you could throw a stone so hard that it would never come back at all? A speed at which it would simply keep going, rising and rising, escaping the pull of the Earth forever, out into space? And the answer, it turns out, is yes. There is such a speed, and we call it the escape velocity. And every world has one. For our Earth, it is a little over 11 kilometers every second, which is fast, unimaginably fast by everyday standards, something like 40,000 kilometers an hour. Throw a stone that fast, straight up, and it will never fall back. It will simply leave out into the dark forever. That is why rockets must burn so furiously and so long to reach space. They are climbing out of the deep pit of the Earth's gravity, and to escape it entirely they must reach that great speed. Now here is where it becomes interesting. The escape velocity depends on the world you are standing on. A bigger, heavier world pulls harder, and so you would have to throw the stone faster to escape it. On the Moon, which is small and light, the escape velocity is much lower, only a few kilometers a second, so a very strong throw could send a stone off the Moon entirely. On an enormous planet it would be far higher, and on a star more massive still, higher again. And it depends too on something less obvious, which turns out to matter enormously for our story. It depends not only on how heavy the world is, but on how tightly that weight is packed. Because what really counts is how close you can get to all that mass. Stand on the surface of a great, puffy world, and you are already very far from its center, with much of its bulk spread out around and beneath you at a distance, and its grip on you is correspondingly gentler. But squeeze that same amount of matter down into a much smaller ball, and now you can stand right up against it, far closer to the center than before, with all of that mass concentrated just beneath your feet. Nothing has been added, not 1 gram more. And yet the pull at the surface is far stronger, and the speed you would need to escape is far greater, simply because you are so much nearer to all of it. That is the key that unlocks this entire story, and it is worth holding on to as we go. Compression matters as much as weight. Take any object at all and squeeze it smaller without adding anything to it, and the gravity at its surface climbs and climbs. Squeeze it enough, and there is in principle no limit to how strong that surface gravity can become. So here is the question that a thoughtful person, sitting quietly with these ideas, might eventually arrive at. If a heavier and denser object has a higher escape velocity, then what if you imagined an object so massive and so tightly packed that its escape velocity became truly enormous? What if it grew so large that it passed the speed of a bullet, the speed of a rocket, and kept climbing? What if it reached or passed the speed of light itself, the fastest speed there is? What would such an object be? Nothing thrown from it could ever escape, and if light itself could not travel fast enough to climb away from it, then no light would ever leave its surface. It would emit nothing, it would shine not at all. It would be, however massive, however enormous, completely and utterly invisible, a dark star. An object you could never see because no light from it could ever reach your eye. That thought, that precise thought, was written down more than 200 years ago by an English country clergyman who was also a fine and careful scientist, a man of quiet brilliance who has been largely forgotten. He worked through the mathematics of it as it was then understood, and he calculated how large and how dense a star would have to be for its escape velocity to exceed the speed of light. And he concluded that such objects might well exist out there in the heavens, invisible, dark, betraying themselves only by their gravitational pull on the things around them, which is, remarkably, very close to how we would actually find them 2 centuries later. He suggested that if such a dark star had a companion star orbiting it, we might notice the companion swinging around apparently nothing at all, and so detect the invisible by watching the visible dance around it, which is precisely, almost exactly, what astronomers would eventually do. And a few years later, on the other side of the channel, one of the great mathematicians of the age arrived independently at much the same idea and wrote about these invisible bodies too, these great dark suns whose light could never reach us. Picture that first man for a moment, because I find him rather wonderful, and history has been unfairly quiet about him. A clergyman in a country parish, going about his ordinary duties, tending to his congregation, and in his spare hours doing science of the first rank. He was one of those figures the age produced now and then, a person of enormous ability, working quietly away from the great centers of learning, thinking deeply, publishing occasionally, and arriving at conclusions decades ahead of everyone. He made real contributions in several fields, and among them, almost in passing, he sat down and reasoned his way to the possibility of invisible stars, objects so profoundly heavy and so tightly packed that their own light could never leave them. He had no telescope capable of testing it. He had no evidence of any kind. He had only the laws of gravity, some careful arithmetic, and a willingness to follow the reasoning wherever it happened to lead, even somewhere as peculiar as this. And that willingness, that readiness to take an idea seriously simply because the mathematics supports it, however strange the destination, is one of the great engines of discovery. It appears again and again in this story. It is, in a sense, the whole of this story. Rest there a moment and feel how remarkable that is. More than 200 years ago, with nothing but pen and paper and the laws of gravity as they then stood, two thoughtful people worked out that the universe might contain objects so massive that light could not escape them, invisible bodies lurking in the dark. They had no evidence. They had no way to look. They simply followed the logic where it went, and it took them to a very strange place indeed. And then, quietly, the idea faded away and was almost entirely forgotten for well over a century. Why? Because the understanding of light itself changed. In the years that followed, evidence mounted that light was not made of little particles, tiny corpuscles that could be slowed by gravity like a thrown stone, but was instead a wave, a ripple traveling through space. And if light was a wave, then the whole argument seemed to collapse because it was not at all clear that gravity should affect a wave of light in the way it affects a stone. The dark star idea rested on treating light like a thrown pebble. And once that picture fell out of favor, the idea lost its foundation and slipped away into obscurity, a curious footnote in old papers, unread, unremembered. So the first dawning of the idea came and went, and the universe kept its secret for another 100 years and more, waiting for someone to arrive with a completely new picture of gravity itself. And when that person came, at the beginning of the last century, everything changed and the black hole was born again, in a form far stranger and far more beautiful than any dark star. Let us come, then, to the Great Revolution, and to the man whose name everybody knows. For more than 2 centuries, our understanding of gravity had rested on the work of the great English physicist who had first described it mathematically, the man of the falling apple. In his picture, gravity was a force, a pull, an invisible attraction reaching across empty space between any two objects, drawing them toward one another. It was a magnificent theory. It explained the falling of stones and the orbits of the planets with astonishing precision, and it stood, unchallenged, for over 200 years, one of the greatest achievements of the human mind. And then, a little over 100 years ago, a patent clerk turned physicist reimagined the whole thing from the ground up and gave us something entirely different. His idea, and it is one of the most beautiful ideas anyone has ever had, was that gravity is not a force at all, not a pull, not an invisible rope, not an attraction reaching across the void. Gravity, he said, is the shape of space itself, or more precisely, the shape of space and time together, woven into a single fabric. Let me try to give you a feeling for it gently, because it is a strange and lovely picture, and it lies at the heart of everything that follows. Imagine a large sheet of stretched rubber, held taut like a trampoline. If nothing is on it, the sheet is flat, and a marble rolled across it travels in a straight line, on and on. Now place something heavy in the middle of the sheet, a bowling ball, and the sheet sags, dips, curves downward around the weight. And now roll your marble across it again. It no longer travels in a straight line. As it passes near the dip, it curves, bending its path around the heavy object. And if you roll it just right, it will circle round and round the dip, orbiting, held in place not by any rope or pull, but simply by the shape of the surface it is rolling on. That, in a rough and imperfect picture, is what he proposed the universe is truly like. Mass and energy bend the fabric of space and time around them, and everything else moves along the curves that result. The Earth does not orbit the Sun because the Sun is pulling on it with some invisible force. The Earth orbits the Sun because the Sun's enormous mass has bent the space and time around it into a great smooth valley, and the Earth is simply traveling in the straightest possible line through that curved landscape, which happens to be a circle. There is no pull. There is only shape, and things moving freely through it. Rest there a moment with that idea, because it is one of the loveliest thoughts in all of science, and it rewards a little quiet. Space is not an empty stage on which things happen. It is a thing in itself, a fabric that can bend and stretch and ripple. The presence of matter shapes it, and the shape of it guides the motion of everything within. The planets in their long, slow orbits, the moon around the Earth, the falling of a leaf. All of it is not pulling but shaping, the geometry of a universe gently curved by everything it contains. And there is a second half to the idea, which the rubber sheet cannot show you, and which will matter enormously later. It is not only space that bends, it is time as well. The two are woven together into a single fabric, and when a great mass curves that fabric, it curves both threads at once, which means that near a heavy object, time itself runs slower. Not slower in the sense of seeming slower or feeling slower, actually slower. A clock sitting at the bottom of a deep gravitational valley truly ticks fewer times than an identical clock far away in empty space. A person living their whole life at sea-level ages by an almost unmeasurably tiny amount, more slowly than a person living on a mountain top. This is not a theory or a manner of speaking. It has been measured, with clocks precise enough to detect the difference over a few flights of stairs, and it is true. And it is one of the strangest facts about the world we live in. Hold on to that gently as we go, because if a modest mass like our Earth slows time by a whisper, then the question naturally follows. What happens to time near something vastly heavier and vastly more compressed? How slow can it go? And what would happen at a place where the curving became so extreme that it went beyond every limit? We will come to that. But sit with it for a moment first, the sheer strangeness of it, that time is not a fixed and universal thing marching everywhere at the same rate, but a local quality of a place, running faster here and slower there, shaped by the weight of everything around it. And this new theory did not merely restate the old one in fancier language. It made new predictions, things the old picture did not say, and they could be tested. It predicted that light itself, passing near a massive object, would follow the curve of the bent space and be deflected. And this was measured during a great eclipse and found to be true. It predicted small deviations in the orbit of the innermost planet that the old theory could not account for. And there they were. It predicted that time itself would run more slowly deep in a gravitational valley. And this too has been measured again and again and is true, and is accounted for every day in the satellites that guide us. The new theory was right. Space and time really do bend. But it had a consequence that nobody, least of all the man who devised it, was prepared for. Within a few months of the theory being published, while the Great War raged across Europe, a German physicist serving at the front, doing his calculations in the gaps between his duties on the Eastern Front, solved the theory's central equations for a simple case: a single spherical mass sitting alone in space. He worked out exactly how such an object would curve the space and time around it. He sent his solution back, and it was a beautiful and important piece of work, and it described precisely how a planet or a star bends the fabric around itself. Sit with that picture for a moment, because it is one of the more haunting scenes in the history of science. A man in his 40s, already an accomplished astronomer, who had volunteered for service and found himself in the mud and noise of the Eastern Front, calculating artillery trajectories for the army. And there, amid all of that, he obtained a copy of the new theory, freshly published back home, and read it and set to work on it in whatever quiet hours he could find. The equations at the heart of that theory were fearsomely difficult, and their author had assumed it would be a long time before anyone found an exact solution to them. Within weeks, this man at the front had found one and sent it back, and received in reply a letter of frank astonishment. And then, within a year, he was dead. He had contracted an illness while on service, and it killed him within months of his great achievement. He never learned what his solution truly contained. He never knew that hidden inside those few lines of mathematics, worked out in the gaps between his duties in a war zone, was the first proper description of the strangest object in the universe. The thing is named for him now, that critical radius, and his name is spoken every day by physicists all over the world, and he died without ever knowing. But hidden in that solution was something very strange indeed, because the mathematics said that if you took a given amount of mass and squeezed it into a small enough ball, something extraordinary happened. There was a certain radius, a certain size, depending on the mass, and if the object was squeezed down smaller than that, the curvature of space around it became infinite. The equations broke. Space and time, in that solution, curved so severely that they closed in upon themselves and formed a boundary, a surface of no return, beyond which nothing could ever come back out. That radius, that critical size, would come to be called by his name, and it is a real and central thing in this story. For our sun to become such an object, you would have to crush the whole of it. That vast glowing sphere more than 1,000,000 times the volume of the Earth, down into a ball just a few kilometers across. For our own Earth, you would have to squeeze the entire planet, every mountain and ocean and continent, down into a sphere the size of a small marble, less than 2 centimeters across. Squeeze anything past that limit, and the mathematics said it would vanish behind a boundary from which no light, no matter, no signal of any kind could ever return. It was, in the language of the new theory, exactly the dark star reborn, but far stranger, because this was no longer just a matter of light failing to climb away. This was space and time themselves folding shut, sealing off a region of the universe from the rest, permanently and completely. And the difference between those two pictures matters, so let me draw it out gently, because it is the heart of what makes these objects so profoundly strange. In the old picture, the dark star was simply a very heavy object whose light could not get away. If you were somehow able to travel fast enough, you could still leave. The light was merely too slow to climb the hill. The hill was steep, but it was still a hill. In the new picture, it is not a hill at all. The boundary is not a place where escape is difficult. It is a place where escape has stopped being a direction. Space is curved so severely there that every possible path leading away from the center has been bent around to point back inward. It is not that you cannot travel fast enough to leave. It is that leaving is no longer somewhere you can go, in the same way that yesterday is no longer somewhere you can go. Once past that boundary, every road, no matter which way you steer, leads deeper in. Moving away from the center becomes as impossible as moving backward through time. That boundary has a name, and it is one of the loveliest names in all of science. We call it the event horizon. A horizon, because like the horizon on the sea, it is a limit to what can be seen, a line beyond which the world is hidden from us. And events, because what lies past it is not merely invisible, but permanently disconnected. Anything that happens beyond that surface can never affect us, never reach us, never be known to us in any way. It is not that we lack the instruments to observe it. It is that no signal from there can ever in principle arrive. Whole histories could unfold beyond that horizon, and they would be as inaccessible to us as if they had never happened at all. And here is what I find most human and most touching about this whole story. Almost nobody believed it. Not for decades. The mathematics said such objects could exist, and the greatest physicists in the world, including the very man whose theory it was, simply did not accept that nature would ever actually make one. They had various reasons. Some thought the strange boundary was merely a mathematical artifact, an illusion produced by an awkward choice of coordinates, not a real feature of the world. Others thought that no real object could ever be squeezed that small, that something would always intervene, that some pressure or force would halt the collapse before it reached that terrible threshold. The theory's own author wrote a paper arguing that such objects could not form in reality, that nature would find a way to prevent it. It felt wrong to them. It felt too extreme, too absurd, too much like a flaw in the theory rather than a truth about the universe. Rest a moment there and feel the very human shape of that. These were not foolish people. They were among the finest minds our species has produced, and they had every reason for caution. But the mathematics was telling them something so strange that they could not bring themselves to believe it, and so they looked for reasons why it could not be so. It is one of the recurring patterns in the history of science, this resistance, this deep reluctance to accept that the universe might really be as strange as the equations insist. And it is not a failing exactly. It is caution, and caution is often right. But sometimes the universe truly is that strange, and then the resistance simply delays the discovery, sometimes for decades. And so the question became, could a real star actually collapse that far? And this is where the story takes a turn that is both scientifically thrilling and, in human terms, rather sad. The question of what happens to a star when it dies had begun to be understood. A star, while it lives, is a balance, a long, slow standoff between two opposing tendencies. Its own enormous gravity is forever trying to crush it inward, to pull all that mass toward the center. And the furious nuclear fire burning in its core is forever pushing outward, holding the star up against its own weight. For millions or billions of years, these two hold each other in balance, and the star shines steadily. But the fuel is finite. Eventually, the fire in the core falters and dies. And when it does, there is nothing left to hold the star up. And gravity, which never rests and never tires, finally wins. And the star collapses in upon itself. There is something quietly beautiful in that balance when you sit with it. Every star you have ever seen in the night sky is caught in the middle of that same long argument, gravity pulling inward, fire pushing outward, and the two so exactly matched that the star holds its shape and shines steadily for billions of years. Our own sun has been holding that balance for nearly 5 billion years already, and will hold it for about 5 billion more. What looks like the most permanent and unchanging thing in the sky is in truth a slow-motion struggle, paused at the moment of perfect equilibrium, and every star is simply an argument that has not been settled yet. But every star will lose that argument in the end because only one side of it can run out of strength. Gravity never tires. Gravity has no fuel to burn. It simply pulls and pulls, patiently for as long as the mass exists, and it is perfectly willing to wait 1 billion years. The fire, on the other hand, is finite, and so the ending is written into every star from the moment it is born. What then? Scientists had found that for many stars, the collapse is halted. The matter is crushed down into something extraordinarily dense, a burnt-out ember of a star. And there it stops, held up not by fire but by a subtle and deep property of matter itself, a resistance that appears when particles are packed too tightly together. Such objects are real, and we see them, dim and dense and slowly cooling, the corpses of ordinary stars. A spoonful of that material would weigh as much as a truck. Our own sun will end that way in about 5 billion years, its outer layers drifting off into space, and its core left behind as a small dense cinder, roughly the size of the Earth, cooling slowly in the dark for longer than the universe has so far existed. But then a young man, only 19 years old, traveling by ship from India to England to begin his studies, did a calculation on that long voyage that would change everything. Picture the scene, because it is a lovely one. A very young man, brilliant, largely self-taught in the newest physics, leaving his home and his family behind for the first time, on a steamship crossing the Arabian Sea and then the Mediterranean, weeks and weeks of open water with nothing much to do. Most passengers would read or walk the deck or watch the water go by. He worked on the physics of dying stars in his cabin, on the long, slow days at sea, a teenager with a pencil, doing mathematics that nobody had done before. He worked out, using the newer physics of the small, what would happen if the dying star were more massive. And he found something startling. He found that this resistance, this force that halts the collapse, has a limit. If the collapsing star is heavier than a certain amount, somewhat more than the mass of our sun, then that resistance is not enough. Gravity overwhelms it. And the collapse does not stop. Do you see what that means? It means that for sufficiently heavy stars, there is nothing to prevent the collapse from continuing, nothing to catch the falling matter. The star simply keeps falling inward, smaller and smaller and denser, past every limit. And there is no known force in the universe that can stop it. which means the mathematics of that boundary, that sealed-off region, was not an idle curiosity. Nature would actually make these things. Massive stars at the end of their lives would collapse right through that threshold and vanish behind it. He presented this at a meeting of astronomers, this young man, still in his 20s, and the most eminent astrophysicist in the world at the time, an older and immensely respected figure who had been something of a mentor to him, stood up immediately afterward and ridiculed the work in front of the assembled scientists. He declared that there must be some law of nature to prevent a star from behaving in such an absurd way. He was charming and witty and utterly dismissive, and the room, deferring to his great authority, went along with him. It was a devastating moment for the young man, publicly humiliated by his own mentor before the leading figures of his field. And it had consequences. The older man was so respected that his judgment effectively closed the question for years. The young scientist eventually turned his attention to other problems and left the subject behind, moving to another country, building a long and distinguished career in other areas of astrophysics. He was right, of course, entirely right. The limit he calculated is real, and it bears his name to this day, and it is one of the foundational numbers in the study of dying stars. Decades later, long after his elder had died, the world came around and he was honored with the highest prize in physics, in his 70s, for the work he had done as a teenager on a boat. But it took a lifetime, and the delay cost the field years of progress, all because a brilliant young person was told, by someone he admired, that the universe simply could not be that strange. Rest there a moment gently, because there is something quietly moving in that story and something worth carrying. The universe was, in fact, exactly that strange. The equations had been right all along, and the resistance of even the most brilliant minds, the deep human reluctance to accept an answer that feels too outlandish, held the truth at bay for decades. But only for decades, because in the end, the universe is what it is, regardless of what any of us are willing to believe, and the truth waits patiently in the mathematics, in the sky, until we are finally ready to see it. So by that point, the pieces were nearly all in place, scattered across a century and a half of thought. The old idea of a body so massive that light could not escape it. The new understanding that gravity is the bending of space and time. The mathematical solution, showing that a sufficiently compressed mass would seal itself off behind a boundary of no return. And the calculation, showing that dying stars above a certain weight would have nothing to stop them collapsing right through that boundary. Everything necessary had been worked out, and yet almost nobody believed such things really existed. They had no name yet. They had never been seen. They lived only in the equations, dismissed by most of the great figures of the age as a mathematical curiosity that nature would surely never trouble to build. What happened next, how the idea was finally taken seriously, how it was given the name we all know, and how astronomers began, at last, to hunt for these invisible things in the darkness and actually find them, is where we will go next time. But not tonight. Tonight, let the story rest here. In the years when black holes were still only an idea, a strange whisper in the mathematics, unbelieved and unnamed, waiting quietly in the equations for the world to be ready. So let your breathing slow, and let the stone thrown into the air, and the country clergyman with his dark stars, and the sheet of curved space, and the young man calculating on a ship, all grow soft and dim and far away. It was all so long ago now, those patient thinkers, bent over their pages, following the mathematics into places that frightened them. They have all long since laid down their pens and gone to their rest, having passed the puzzle on, as we all do, to the ones who came after. There is nothing here you need to hold or carry tonight. It is only a story, a quiet story about the slow dawning of an almost unbelievable truth, told to carry you gently down into sleep. Let the strangeness of it settle over you softly, the thought of a universe with places in it where space folds shut, and let it be, for now, simply beautiful, and very, very far away. And they are far away. That is worth saying as you drift, because a mind at the edge of sleep can sometimes take a strange idea and turn it into something looming. So let me set it down plainly for you. The nearest of these objects is thousands of years of traveling light away from where you are lying, an emptiness so vast that our fastest craft would need longer than our entire species has existed to cross even a small part of it. They do not wander. They do not approach. They sit where they are, held in their long, slow orbits around the center of the galaxy, exactly as the stars do, and they will still be sitting there, quietly, long after tonight, and every night any of us will ever see. What they truly are from where you are lying is a wonder, something the universe contains that we managed, against all likelihood, to work out from a few pages of mathematics before anyone had ever seen one. That is the marvel worth taking into sleep with you, not the darkness of the thing, but the light of the discovering. Sleep now, warm and safe and held, here on this small blue world, where gravity is gentle and the ground is solid and nothing at all is falling. Outside your window, the sky is turning slowly, as it always has, the same stars our ancestors watched, and everything out there is exactly where it should be, and nothing anywhere requires anything of you tonight. The story will still be here tomorrow and the night after, and we have all the time in the world to follow it gently, together into the dark. Last time we left them waiting in the mathematics, unbelieved and unnamed. We had followed the idea all the way from its first faint appearance, more than 2 centuries ago, in the mind of a country clergyman, imagining stars so heavy that their own light could not leave them. We had watched that idea fade and be forgotten, and then reappear in far stranger form, when gravity itself was reimagined as the bending of space and time. We had seen the solution worked out in a war zone by a man who died before he understood what he had found, and we had seen a young scientist on a ship calculate that heavy stars, at the end of their lives, would have nothing left to stop them collapsing forever, and then be publicly ridiculed for it by his own mentor. So the pieces were all there, and still, almost nobody believed it. These objects had no name. Nobody had seen one. Nobody expected to. The great figures of the age had looked at the equations and looked away, and decided that the universe would surely never be so extreme. Tonight, that changes. Tonight we follow the long, slow turning of the tide across the middle of the last century, as the idea was taken seriously at last, given the name we all know, and then, most wonderfully of all, actually hunted for in the darkness of the sky and found. Tonight, black holes stop being mathematics and start being real. But before we begin, let me ask you again gently, as I will each night. If these quiet journeys through the mysteries of our universe help you set down your day and find your way toward rest, then please take just a moment to subscribe. It is one small tap, but it means the next of these will find its way back to you on some future restless night, and it helps, more than you might know, to keep these stories being made for you and for all the others out there in the dark tonight. So if you would subscribe and stay with me, night after night, as we wander on together through the great slow stories of how we came to understand our world. And tell me, if you will, from wherever you are resting tonight, where you are listening from, and what hour it has reached where you are. Leave it in the comments below. It is a lovely thing to see all the places and all the hours gathered there, all of us drifting off together beneath the same turning sky. And now, let your shoulders come down, and let your breathing slow, and let the whole weight of your day loosen and fall away. Come with me back out into the dark, to where we left the story, and let us watch the impossible slowly become real. Let us begin with the paper that nobody read. At the very end of the 1930s, just as the world was falling into war, 2 physicists in America sat down and did the thing that everyone else had avoided. They took the young man's calculation seriously. They accepted, for the sake of argument, that a heavy star at the end of its life would have nothing to hold it up. And they asked simply and directly, what happens then? What does that collapse actually look like? Not in vague terms. In detail, worked all the way through, using the full theory of curved space and time. And they found that the collapse does not stop. It cannot stop. Once a star heavy enough runs out of fuel, it falls inward and keeps falling, and every possible thing that might catch it fails in turn, and it goes right through that critical radius and seals itself off behind the horizon, exactly as the mathematics had been quietly insisting for 20 years. The star, from the outside, appears to slow as it approaches the boundary, its light growing dimmer and redder, its motion seeming to freeze until it fades from view entirely and simply is not there anymore. And a region of absolute darkness is left behind, cut off from the rest of the universe forever. And that detail, the apparent slowing, is one of the strangest and most beautiful things in this whole story, and it comes directly from what we said last night about time. Remember that time runs more slowly deep in a gravitational valley. Near a collapsing star, the valley becomes so deep that the effect grows enormous. So if you were watching from a safe distance, you would not see the star vanish in an instant. You would see it fall and slow further. And the closer its surface came to that critical boundary, the more sluggish everything about it would appear, until it seemed to hang there, almost motionless, hovering just above the edge, its light draining away to red and then to nothing. You would never actually see it cross. From outside, the crossing takes forever. The star simply fades, over a fraction of a second, into invisibility, frozen at the threshold for all eternity as far as any outside observer is concerned. That is why they were briefly called frozen stars. And yet, from the point of view of the star itself, or of anyone unfortunate enough to be falling with it, nothing of the sort happens. The fall is quick and continuous, and the boundary is crossed without any fuss at all, without even anything to mark the moment. Two entirely different accounts of the same event, both completely true, differing only in where you happen to be standing. That is what it means to live in a universe where time is a local thing. It was the first proper description of how a black hole actually forms in the real world, out of a real dying star. And it was correct in its essentials, and it stands today as one of the landmark papers in the history of physics. Almost nobody noticed. And here is where history does something extraordinary and rather sad. That paper was published in the first days of September in 1939. If you know your history, you will know what else happened in the first days of September in 1939. The German army crossed into Poland and the world went to war. And so the paper that first described the birth of a black hole appeared in the same week that the whole of civilization turned its attention to something else entirely. Physics, in particular, was swept up completely. Nearly every capable physicist in the world was pulled into war work, into radar, into ballistics, into the great secret project to build a weapon from the atom. And the man who had written that paper became the scientific leader of that project and spent the next several years in a desert laboratory, occupied with something very far from the deaths of distant stars. The study of collapsing stars simply stopped. For most of the 1940s, and well into the 50s, almost nothing happened. The idea sat there, published, correct and unread, waiting out the war and its long aftermath, while the people who might have carried it forward were building other things. Rest there a moment and feel the strange shape of that. One of the great discoveries about the nature of the universe, arriving in the exact week that the world stopped listening. It is a reminder of how much of science depends on timing, on attention, on whether anyone happens to be free to look. The truth was there, printed, available in any good library for 20 years. It simply had to wait until somebody had the time and the inclination to pick it up again. And when they finally did, in the early 1960s, everything happened at once. What followed is often called the Golden Age, and it was a remarkable flowering. A new generation of physicists, young, unburdened by the old resistance, came to the theory of curved space and time, and found it full of unexplored country. Better mathematical tools had been developed, and crucially, these were people who had not spent their careers insisting that such objects could not exist. And so they were free to simply ask what the equations said and follow them. And they found extraordinary things. One of them proved something that settled the argument once and for all. The old objection had always been that a real star is messy. It is not a perfect sphere. It spins. It is lumpy and turbulent and irregular, and the hope had been that all this messiness would somehow save it, that a real lopsided spinning star would collapse to one side or swirl or bounce, or in some way avoid the terrible fate that the clean idealized mathematics predicted. This young mathematician proved, elegantly and generally, that it does not matter. Given certain broad conditions, once a collapse passes a certain point, No amount of messiness or spin or irregularity can save it. The collapse to a point is unavoidable. It is not an artifact of simplified assumptions. It is what actually happens. And notice what that proof was really saying, because it is quite unsettling once you sit with it. It was not only saying that the horizon forms, it was saying that inside, the falling matter does not settle down into some very small, very dense ball and stop. It keeps going. It is crushed down toward a single point of zero size and infinite density, a place where the curvature of space and time becomes infinite, and the equations themselves stop producing meaningful answers. Physicists call that a singularity, and it is worth being honest about what the word actually means. It does not mean we have discovered a point of infinite density sitting inside every black hole. It means our theory breaks. Infinity is not an answer in physics. Infinity is what appears on the page when a theory has been pushed past the limits of where it applies, and is telling you, politely, that you need a better theory. So the true situation, right down at the center, is that nobody knows. We have two magnificent theories, one describing gravity and the shape of space at the largest scales, and another describing matter and energy at the smallest, and they have never been successfully joined. Almost everywhere in the universe this does not matter, because gravity is weak where things are small and things are large where gravity is strong. The center of a black hole is the one place where both are true at once, where an enormous mass is crushed into a vanishing volume, and there the two theories are forced to meet, and they contradict each other. Which means that hidden inside every black hole is not simply a very dense object, but an unanswered question, one of the deepest we have. It has stood open for a century now, and there is something rather wonderful about that when you think of it. The universe has kept one secret perfectly sealed, behind a boundary that no message can cross, and left the question sitting there patiently for whoever eventually works it out. Another found the solution for a spinning black hole, which turned out to be far more complex and far more beautiful than the simple non-spinning case, and far more relevant too, since everything in the universe spins. This solution described a black hole that drags the very fabric of space around with it as it turns, swirling space itself like water circling a drain, and it remains one of the most remarkable pieces of mathematics in all of physics. And there was another discovery, stranger and more elegant than either, which is worth a moment of your night because it is so beautifully simple. It turns out that black holes are, in a sense, the simplest objects in the entire universe. Think about how much information it would take to fully describe an ordinary star. Its mass, its size, its temperature, its chemistry, the swirling patterns of its surface, the layers of its interior, the magnetic fields threading through it, its whole long history, endless detail. Now take that star and collapse it into a black hole, and almost all of that detail simply vanishes. It turns out that a black hole can be completely described by just three numbers: how much mass it has, how fast it spins, and how much electric charge it carries, which in practice is always essentially zero. That is all. Two numbers, really, for any black hole in the real universe, which means that two black holes with the same mass and the same spin are exactly identical in every measurable respect, even if one formed from a giant star and the other from something else entirely. All the individuality of whatever fell in, all its history and structure and complexity, is erased, hidden away behind the horizon where it can never be examined. There is a phrase for this, coined during those years, and it is one of the great phrases in physics. Black holes have no hair, meaning no features, no distinguishing details, nothing individual about them at all. Just mass and spin and otherwise perfect featureless simplicity. Rest a moment with that, because it is such a strange kind of beauty. The most extreme object in the universe, the place where all our physics strains and breaks, is also the plainest thing there is. A star has a biography. A black hole has only a weight and a spin. Everything else it ever was has been folded away out of sight, and it was during those same years that these objects finally got their name. For decades they had been called by clumsy phrases: collapsed stars, frozen stars, because from the outside the collapse appears to freeze at the boundary. Objects in a state of continued gravitational contraction, which is accurate and entirely unusable. The field badly needed a name, And in the middle of the 1960s, at a conference, someone in the audience apparently called out the phrase black hole, and one of the most influential physicists of the age heard it, liked it, and began using it. He was a great namer of things, this man, and he understood something that many scientists miss, which is that a good name is not a decoration, but a tool. A vivid name makes an idea thinkable. It lets it be discussed, argued over, taught to students, printed in newspapers. He used the phrase in a lecture and then in his writing, and within a couple of years it had spread everywhere and become permanent, and you can feel why it worked. Black hole. Two short plain words and instantly you have a picture. It sounds like what it is. It is faintly frightening and memorable, and it needs no explanation. It escaped from physics into ordinary language almost immediately, and today it is one of the very few pieces of advanced physics that essentially everyone has heard of. The idea had existed, in one form or another, for nearly 200 years, and had been mathematically solid for 50, and it took a good name to finally make it real in the public mind. There is a real lesson in that, and it applies far beyond physics. An idea that cannot be said easily tends not to be thought about easily either. As long as these objects were called things like bodies in a state of continued gravitational contraction, they remained the property of a small circle of specialists, difficult to raise at a dinner table, impossible to put in a headline. Give them two plain syllables that anyone can picture, and suddenly students want to study them. Newspapers want to write about them. Funding bodies want to pay for telescopes to look for them, and children lie awake thinking about them. The name did not change the physics by so much as a comma. It changed how many people were thinking about the physics, and that turned out to matter enormously. But a name is not evidence, and through all of this, all the beautiful mathematics of the Golden Age, one enormous question remained entirely open. Do these things actually exist? Is there one anywhere out there in the real universe? Or is this all a magnificent castle built purely in the air? Nobody knew, and finding out looked close to hopeless. How on earth do you find an object that emits no light? The entire history of astronomy from the beginning had consisted of collecting light. Light from stars, light from planets, light from distant glowing clouds of gas. Every single thing we knew about the universe beyond our own solar system, we knew because light from it had arrived at our eyes. And here was an object defined by the fact that no light can ever leave it. It is not dim. It is not faint. It is absolutely perfectly invisible forever. And yet, within about a decade, astronomers found them. Not because the black holes gave themselves away, but because of what they do to everything around them. The first clue arrived from an unexpected direction, and at first nobody understood what they were looking at. In the early 1960s, astronomers using the new radio telescopes had catalogued a number of odd objects that gave off powerful radio waves. Some of these seemed to line up with faint points of light that looked, through a telescope, like ordinary stars. That was already peculiar, since ordinary stars do not blaze in radio waves. They were given an awkward name meaning star-like radio sources, which was eventually shortened to quasars. Then someone managed to take a proper reading of the light from one of them and got a result so bizarre that the pattern in it made no sense at all. It matched no known chemistry. It sat on his desk for months, an unsolved puzzle, and then one afternoon he saw it. The pattern was completely ordinary hydrogen, the commonest substance in the universe. It only looked strange because it had been shifted enormously, far more than anyone had thought possible. Light stretches when its source is moving away from us, and because the universe is expanding, the further away a thing is, the faster it is receding, and the more its light is stretched, so the amount of stretching tells you the distance. And the stretching in that light was so extreme that the object had to be unimaginably far away, hundreds of millions of light years distant, and later examples turned out to be billions. Now hold both facts together and feel the problem. This object was billions of light years away, and yet it was still bright enough to be photographed from Earth and mistaken for a nearby star. To appear that bright from that distance, it had to be pouring out energy on a scale that beggars description. A single one of these objects could outshine an entire galaxy of 100 billion stars by a factor of tens or hundreds. And then came the detail that made it truly impossible. These objects flickered, their brightness varied noticeably over weeks, sometimes days, and that is a devastating constraint, because nothing can change its brightness faster than light can cross it. If an object dims over the course of a day, then it cannot be more than about a light day across, or the far side would not have got the message yet, which meant that these quasars, outshining whole galaxies, were smaller than our own solar system. The energy of 100 billion stars pouring out of a region smaller than the orbits of our own planets. No ordinary process could do that. Not nuclear fusion, not anything known. There was only one mechanism anybody could think of that was violent enough, and it was the one thing nobody had wanted to believe in: gravity. Matter falling into something enormously massive and enormously compact, because when matter falls toward a black hole, it does not simply drop straight in. It swirls, forming a vast flattened disk of gas spiraling inward, and as it spirals, it is compressed and torn by friction and heated to unimaginable temperatures, millions of degrees, and it blazes ferociously. The falling matter converts a staggering fraction of its mass into pure radiation before it crosses the horizon and disappears, far more efficiently than the nuclear fires inside stars. Let me give you a picture of that, because it is one of the great sights of the universe, even though no human eye has ever seen it directly. Imagine a vast whirlpool of glowing gas, wider than our entire solar system, flattened into a disk like a record on a turntable, turning around a small central darkness. The outer parts drift inward slowly, gently, taking their time. But as the gas spirals closer, it moves faster and faster, and the layers rub against each other, and the friction heats it. And the inner regions become so hot that they blaze white, then blue, then pour out X-rays. And right at the very center, where the disk ends and the darkness begins, the glowing gas simply stops. There is a hole in the middle of all that light, perfectly round, absolutely black, and everything that crosses that edge is gone. That is what powers a quasar. Not the black hole itself, which gives out nothing at all, but the enormous shining whirlpool of matter falling into it, glowing with the energy it loses on the way down. And that is the great irony at the heart of this whole story, the thing that turns the problem inside out. The blackest objects in the universe power the brightest lights in it. You cannot see the black hole, but you can see from the far side of the universe the light of everything falling into it screaming as it goes. Rest there a moment and hold that, because it is one of the loveliest reversals in all of science. For years the objection had been that these objects were undetectable by definition, invisible forever, beyond all hope of observation. And it turned out the opposite was true. The regions around them are the most luminous things that exist. Far from being invisible, they are practically shouting, and we had been photographing their light for years without understanding what we were seeing. At the center of a quasar, we now know, sits a black hole of monstrous size, millions or billions of times the mass of our sun, feeding on the gas of its host galaxy. And such things sit quiet and mostly starved now, at the centers of nearly all large galaxies, including our own. But the quasars were far away, and the argument was indirect, and many were unconvinced. What was needed was something closer, something in our own galaxy that could be studied properly, and to find it, astronomers had to learn to look at the sky with entirely new eyes. Here is the thing about our atmosphere. It is wonderful and it keeps us alive, and it also blocks almost everything. Visible light comes through and radio waves, which is why we have eyes and radio telescopes. But most of the rest of the spectrum is absorbed high above us and never reaches the ground. In particular, X-rays, produced by the hottest and most violent processes in the universe, are stopped completely. For the whole history of astronomy, we had been looking at the sky through a narrow crack, and the most violent things in the universe were invisible to us, not because they were faint, but because our own air was in the way. So in the 1960s, astronomers began putting detectors on rockets, brief suborbital flights that would climb above the atmosphere and get a few minutes of unobstructed observation before falling back, a few minutes at a time. And in those stolen minutes, they discovered that the sky in X-rays is a completely different place. It is full of blazing sources that nobody had ever suspected, violent and hot and utterly invisible from the ground. Think about how strange that must have felt. Humanity had been looking at the night sky for as long as there have been humans. Every civilization that ever existed had mapped it, named its patterns, built its calendars and its myths around it. We thought we knew the sky better than almost anything. And then, in the space of a few years, we discovered that we had been seeing only a thin slice of it, and that laid over the familiar quiet stars was an entirely different sky, invisible to the eye, full of things blazing furiously in a kind of light our atmosphere had always hidden from us. It is worth carrying that thought gently as you rest. The sky above your roof tonight that you could go out and look at is not the whole sky. It is the part our eyes were built for. Above the air there is more in every direction, and much of it is violent and strange. And it took rockets and satellites to see it, and every one of those discoveries is less than a single human lifetime old. And then, at the start of the 1970s, a satellite was launched to survey the whole X-ray sky properly, from orbit, continuously. It was launched from a platform off the coast of Kenya, on the anniversary of that country's independence, and it was named with the Swahili word for freedom. It found hundreds of X-ray sources, and one of them, in the constellation of the Swan, would become the most famous object in this entire story. It was already known to be an intense X-ray source, and now with better data, astronomers could see that its X-ray output flickered wildly, chaotically, on timescales of less than a second, which meant, by the same reasoning as the quasars, that the source had to be tiny, no more than a few hundred kilometers across. Then they worked out where it was, precisely enough to look at that patch of sky with an ordinary telescope, and they found a large blue star sitting right there. But the star itself was not producing the X-rays. It was an ordinary, if massive, star. So they watched it carefully and measured its motion, and found that it was wobbling, moving in a regular orbit over and over every 5.5 days around something. Around what? There was nothing there, no second star, no light of any kind at that position, and yet the visible star was clearly orbiting a companion. And from the speed and the period of that orbit, they could calculate the mass of the invisible partner. And the answer came back far heavier than the limit above which nothing known can hold a collapsed star up. So here was the situation: an invisible object, too heavy to be any kind of dead star that can support itself, only a few hundred kilometers across, judging by the flickering. Blazing in X-rays exactly as gas would if it were being torn apart and heated as it spiraled into a deep gravitational well. In orbit with a visible companion, whose light gave the whole thing away. And once you understand what is happening there, the picture becomes rather extraordinary. That great blue star is enormous, far bigger and far brighter than our sun, and it sits so close to its invisible partner that its outer layers are being pulled away. A stream of gas flows off the surface of the star, drawn across the gap, and spirals down into a hot, glowing disk around the dark companion. And it is that disk, heated to millions of degrees as it spirals in, that pours out the X-rays we detect from here. The star is being slowly eaten. It has been feeding its dark partner for a very long time, and will go on doing so for a long time yet. Two objects born together, most likely from the same cloud of gas long ago. One of them lived out its life and died and collapsed into darkness. The other still shines, and is slowly being consumed by the corpse of its companion. There is something almost mournful in it, and it is happening right now, tonight, in the constellation of the Swan, and has been happening throughout every year of your life and every year of everyone's life before you. Which is, remarkably, almost precisely what that country clergyman had suggested 200 years earlier, when he wrote that we might detect an invisible star by watching a visible one circle around it. Rest there a moment and feel the shape of that, because it is a beautiful thing. 2 centuries apart. A man in a quiet parish reasoning with pen and paper about invisible stars and how one might find them. And a team of astronomers with a satellite in orbit doing exactly what he described and finding one. The idea had taken 200 years to travel from a thought to an observation, and when it arrived in almost the same form it had started. It was not absolute proof. In science, for something this strange, there rarely is a single decisive moment. There were other possible explanations, increasingly strained ones, and the argument ran on for years. Two famous physicists even made a friendly wager about it, one of them betting against, largely, he later admitted, so that he would have some consolation if his life's work on these objects turned out to be about nothing at all. He conceded the bet years later, when the evidence had become overwhelming. But that object in the Swan was the turning point. It was the first place in the sky that most astronomers were willing to point to and say, there is probably one there. After 200 years as a curiosity and 50 as a mathematical embarrassment, black holes had become, at last, real things with addresses. And once astronomers knew what to look for, they found more. And more. Dozens of similar systems in our own galaxy, visible stars orbiting invisible heavy companions, evidence for enormous ones at the centers of other galaxies. The universe, it turned out, was full of them, and had been all along, and we had simply not known how to see. And they came, it emerged in wildly different sizes, which is one of the stranger facts about them. There are the ones we have been describing, formed from the collapse of single heavy stars, a handful of times the mass of our sun packed into something a few tens of kilometers across. You could drive across one if driving across such a thing were possible in an afternoon. And then there are the others, the ones at the hearts of galaxies, and they are of an altogether different order. Millions of times the mass of our sun, billions in some cases, objects whose horizons are larger than the orbits of entire planetary systems, so vast that light itself, which crosses our whole solar system in a matter of hours, would take a day or more simply to travel across one. Nobody is entirely sure how the largest of them came to be so large so early in the history of the universe, and that remains a live question today. But there they sit, one at the center of nearly every large galaxy we have looked at, including the one we live in. There is one at the heart of our own Milky Way, about 4 million times the mass of the Sun, sitting quietly in the direction of the constellation of the Archer. And it has been there since long before the Earth existed, and it will be there long after. But there was still something missing. Everything so far was inference. Careful, powerful, convincing inference, but inference all the same. We were watching the behavior of other things and deducing the presence of something invisible in the middle. Nobody had ever detected a black hole directly. Nobody had ever seen one. That would take another 50 years, and two of the most extraordinary experiments ever attempted. And it is where our story ends. Next time, we will watch astronomers track individual stars whipping around the invisible heart of our own galaxy for decades. We will hear the sound of two black holes colliding a billion light-years away, arriving here as a tremor in the shape of space itself. And we will see, at last, the photograph. And we will find, in a wonderful final twist, that these objects are not entirely black after all. But not tonight. Tonight, let the story rest here, at the moment when the impossible finally became ordinary, when the equations came down out of the air and settled into the sky, and astronomers looked up and understood for the first time that the dark is not empty. So let your breathing slow, and let the unread paper, and the golden age, and the flickering quasars, and the wobbling blue star in the constellation of the Swan all grow soft and dim and far away. It was all so recent in the great scheme of things, and yet already it has passed into history, and the people who did it have mostly gone quiet or gone entirely, having handed the puzzle on, as we all do, to the ones who came next. There is nothing here you need to carry tonight. It is only a story about people looking very carefully at the dark and slowly realizing what was in it, told to carry you gently down into sleep. Out there right now in the constellation of the Swan, that great blue star is still turning around its invisible partner, as it has for millions of years and will for millions more. Patiently, quietly, whether anyone is watching or not. And that is a rather comforting thought to rest with, I think. All of this happens at a pace that has nothing to do with us. The star turns. The gas spirals slowly inward. The great dark thing at the center of our galaxy sits where it has sat since before there was an Earth, and will sit there long after every one of tonight's worries has been forgotten by everyone. The universe is in no hurry at all. It has never been in a hurry. There is no deadline out there, nothing that needs deciding, nothing waiting on you. So let the sky look after itself tonight. It has managed for 13 billion years without your supervision, and it will manage a few hours more. Sleep now, warm and safe and held, here on this small, solid world, where nothing is falling and nothing is spiraling, and the ground beneath you is exactly where it has always been. The story will still be here tomorrow night, with its ending and its photograph and its final surprise, and we have all the time in the world to follow it gently together into the dark. By the end of the last century, we were almost certain they were out there, but no one had ever seen one. That is where we left the story. We had followed it all the way from a country clergyman imagining invisible stars, through the reimagining of gravity as the shape of space and time, through the long decades of disbelief, and out at last into the sky, where astronomers had found a great blue star in the constellation of the Swan, wheeling around something invisible and heavy and small. We had learned that the darkest objects in the universe power the brightest lights in it, and that black holes come in sizes from a few times the mass of our sun to billions. But every single piece of that was inference. Careful, powerful, overwhelming inference, but inference all the same. We were watching other things and deducing the presence of something dark in the middle. Nobody had detected a black hole itself. Nobody had ever seen one. And a great many thoughtful people assumed that nobody ever would, that these objects were by their very nature beyond the reach of observation, and that we would have to be content forever with looking at their effects on other things. They were wrong. And tonight, we get to tell you how. Tonight, we watch astronomers track individual stars whipping around the invisible heart of our own galaxy for a quarter of a century. We listen to the sound of two black holes colliding, 1 billion light-years away, arriving here as a tremor in the shape of space itself. We look at the photograph, the actual photograph taken only a few years ago, of the edge of one. And at the very end, we find the loveliest surprise in this whole long story, which is that these objects are not entirely black after all, and will not last forever. But before we begin, let me ask you one last time, and as gently as ever. If these quiet journeys through the great mysteries of our universe have brought you a little peace across these nights, if they have helped you set down your days and drift off into rest, then please, take just a moment to subscribe. It is one small tap, but it means the next of these will find its way to you when you need it, and it helps more than you could know to keep these stories being made for you and for all the others out there in the dark tonight, looking for a little rest. So, if you would, subscribe and stay with me night after night as we wander on together through the great slow stories of how our universe came to be understood. And tell me, if you will, from wherever you are resting tonight, where you are listening from and what hour it has reached where you are. Leave it in the comments below. It is a lovely thing to see all the places and all the hours gathered there together, all of us drifting off beneath the same turning sky. And now, one last time, let your shoulders come down, and let your breathing slow, and let the whole weight of your day loosen and fall away. Come with me out into the dark for the last of this story, and let us go and look at the thing that cannot be seen. Let us begin at the center of our own galaxy. Look up on a clear, dark night, far from any town, and you can see the Milky Way, that faint band of soft light stretched across the sky. What you are looking at is our own galaxy, seen from the inside, the combined glow of billions of stars too distant to separate. We sit out in the suburbs of it, on a quiet spiral arm, a very long way from the middle. And the middle, we had come to suspect, held something enormous. But looking at it directly is close to impossible, because between us and the galactic center lie tens of thousands of light-years of dust and gas, thick enough to block almost all ordinary light. The heart of our galaxy is hidden behind a curtain, but some kinds of light get through, and in the 1990s, two teams of astronomers, one in Europe and one in America, set out to do something that sounds almost absurd. They decided to watch individual stars orbiting the galactic center, and to keep watching them, night after night, year after year, for as long as it took. Think about what that requires. These stars are 26,000 light-years away. From here, the region they orbit in is a patch of sky so small you could cover it many times over with a grain of sand held at arm's length. And the orbits take years, sometimes decades, to complete. There would be no quick result. no dramatic evening of discovery. There would only be the slow accumulation of images, one observing run after another, season after season, gradually building up a record of where each star had been. And they did it. For more than 25 years they kept going, through changing technology and changing staff and all the ordinary uncertainties of long-term funding, returning again and again to the same tiny patch of sky, tracking the same few dozen stars, plotting their positions. And they had to solve a problem along the way that is worth mentioning, because the solution is so elegant. Even above the dust, looking at something that's small from the ground is ruined by our own atmosphere. The air above a telescope is always moving, shifting in warm and cool pockets, and starlight passing through it gets smeared and wobbled. That is why stars twinkle, and it is beautiful to look at and disastrous if you are trying to measure the position of a faint star to extraordinary precision. So they used a technique in which the telescope measures how badly the air is distorting the incoming light, hundreds of times every second, and then bends a flexible mirror by tiny amounts, hundreds of times every second, to cancel out the distortion as it happens. Some of these systems even shine a laser up into the sky to create an artificial point of light high in the atmosphere to measure against. Think of that for a moment. A mirror that reshapes itself 1,000 times a second to undo the shimmering of the air, so that a star 26,000 light-years away holds still long enough to be measured. We built that. It works. And without it, none of what follows would have been possible. And slowly over the years, the pattern emerged. Those stars were not drifting randomly. They were orbiting, all of them, around the same central point, in long ellipses, exactly as planets orbit a sun. And the point they orbited was empty. There was nothing there. No light in any wavelength from that position, beyond the faintest whisper. One star in particular became the star of the show. Its orbit is relatively short, only about 16 years, so the astronomers were able to watch it go all the way around and then start again. And it comes in remarkably close at its nearest approach, and when it does, it is traveling at something like 2.5% of the speed of light, thousands of kilometers every second. A star, an entire star, whipping around an invisible point at a speed no planet in our system has ever approached. Imagine watching that over the years. In the early images, it creeps along slowly, taking its time on the long outer part of its path, moving so little from one year to the next that you need careful measurement to see any change at all. And then it begins to gather speed, and the yearly steps grow longer, and it comes racing in toward the invisible center, faster and faster, until it whips around the closest point of its orbit in a matter of months, and goes flying out the other side. And every one of those observations was somebody's night. Somebody drove up a mountain, and set up, and hoped the weather would hold, and took their images and went home. And 25 years of those nights, strung together, became a picture of a star tracing a perfect ellipse around nothing at all. And from the shape and speed of that orbit, you can calculate the mass of the thing at the focus, using mathematics that has been understood since the 17th century. The answer was about 4 million times the mass of our sun, 4 million suns, and it fits inside a region smaller than the orbit of the innermost planet of our own solar system, because the star at its closest passes inside that radius and does not hit anything. There is nothing else it can be. No cluster of stars could be packed that tightly and stay stable. No cloud of dark matter behaves that way. 4 million solar masses in a space that's small has only one answer, and the answer is a black hole, sitting at the center of the galaxy we live in right now tonight, in the direction of the constellation of the Archer. Rest there a moment and hold that image, because it is one of the great images of modern science, and it deserves a little quiet. A handful of astronomers, coming back to the same telescope for a quarter of a century, photographing the same invisible speck of sky, watching a few faint stars creep along their paths, 1 year at a time. It is not glamorous work. Most of those observing nights would have been ordinary or cloudy or frustrating. And out of all that patience came one of the clearest pieces of evidence we have that these objects are real, and that we live in a galaxy with one at its heart. Two of the astronomers who led those teams received the highest prize in physics for that work decades after they began. That is what this kind of science actually looks like. Not a flash of insight, but 25 years of showing up. Now let us turn to something entirely different and far stranger that had happened meanwhile on the theoretical side, because it is the loveliest surprise in this whole story. In the early 1970s, a young British physicist, already living with the illness that would confine him for the rest of his life, was working on what happens when the physics of the very small meets the physics of the very large at the edge of a black hole. And he found something that he did not expect and did not initially believe, and spent some time trying to make go away. He found that black holes are not black. They glow. Very faintly, but they glow, giving off a slow trickle of radiation from just outside the horizon, and in doing so, they very gradually lose mass. Over unimaginable spans of time, a black hole will evaporate. It will shrink and grow fainter, and eventually cease to exist entirely. It is worth saying how faint this glow actually is, because the numbers are almost comic. A black hole formed from a collapsed star has a temperature of something like 100 millionth of a degree above absolute zero. That is far colder than the empty space around it, which means that in the universe as it is today, black holes are actually absorbing far more from the faint background warmth of space than they give off, and so they are growing, not shrinking. The evaporation cannot even begin properly until the universe itself has cooled below the temperature of the black hole, which will take a very long time indeed. And the smaller a black hole is, the hotter and faster it evaporates, which is a strange inversion of how everything else behaves. A tiny one would blaze and vanish in a flash. A great one at the center of a galaxy is colder than anything that has ever existed and will last almost forever. The bigger they are, the slower they go. The reason why is subtle, and I will give you a picture of it rather than the real machinery, because the real machinery lives in mathematics, and this is a story for falling asleep to. But the picture is this. Empty space, according to the physics of the very small, is not truly empty. It seethes. At the tiniest scales, it is constantly producing pairs of particles that appear and vanish again almost instantly, borrowing their existence and paying it back so quickly that nothing is disturbed. This is not a fanciful idea. It has real measurable consequences that have been observed in laboratories. Now imagine that happening right at the edge of a black hole. A pair appears, as pairs always do, but this time, before they can find each other again and cancel out, one of them falls across the horizon and is gone forever. The other is left behind, alone, unable to vanish, and it drifts away into space as real radiation. And the energy for that has to come from somewhere, and it comes in the end from the black hole itself, which is very slightly diminished by the transaction. Do it once and nothing has happened. Do it continuously, over the entire surface of the horizon for eternity, and the black hole slowly bleeds away. And here is the part that gives the whole thing its strange poignancy. The process is achingly slow for anything large. A black hole formed from a collapsed star would take vastly longer than the current age of the universe to evaporate, longer by a factor with dozens of zeros in it. The great ones at the centers of galaxies would take longer still, so long that writing the number down is close to meaningless. The universe is nowhere near old enough for any of this to have happened yet. But it will. Given long enough, and the universe appears to have all the time there is, every black hole eventually fades away, which means that these objects, the most permanent seeming things in all of creation, the places from which nothing ever returns, are themselves temporary. They are not eternal. They are just very, very slow. In the far distant future, long after the last star has burned out and the universe has gone dark and cold, the black holes will still be there, the last structures remaining, shining with their almost imperceptible glow, slowly giving themselves back to the emptiness. And then, one by one, over spans of time that make the current age of the universe look like an eye blink, even they will go. Rest a moment with that, and let it be beautiful rather than sad, because I think it is. Nothing out there is permanent, not the stars, not the galaxies, not even the darkest and heaviest things the universe can build. Everything is on its way somewhere. The difference between a candle and a black hole is only how long the burning takes, and there is a kind of gentleness in that thought on a quiet night that even the most implacable things in existence are, in the end, passing through, exactly as we are. That discovery also opened up one of the deepest unsolved puzzles in physics about what happens to all the information that fell in, whether it is truly destroyed or somehow encoded in that faint escaping glow. Physicists have argued about it for 50 years and are arguing still, but that is a story for another night, and it does not need solving before you sleep. Now let us come to the two great triumphs, both of them so recent that many of you will remember the news. The first is about listening rather than looking. Remember that gravity, in our best understanding, is the bending of space and time. Now, if space can bend, then space can also ripple. If you take two very heavy objects and swing them around each other very fast, they should send out waves, ripples in the fabric of space itself, spreading outward at the speed of light, stretching and squeezing everything they pass through. This had been predicted a century earlier, right at the beginning, by the man who gave us curved space in the first place. And he thought, quite reasonably, that they would never be detected because the effect is so unimaginably tiny. A passing gravitational wave stretches and squeezes space, yes, but by a fraction so small that it beggars belief. How small? Here is the number, and it is worth sitting with. To detect one, you would need to measure a change in length of about 1 part in 10,000 billion billion. If you had a ruler 4 kilometers long, you would need to notice it changing in length by about 1/10,000th of the width of a single proton. That is what was built. Two enormous instruments in different parts of the United States, each consisting of two arms 4 kilometers long, meeting at a right angle, with laser light bouncing back and forth along them, endlessly comparing the length of one arm against the other with a precision that had no precedent in the history of measurement. Decades of work, enormous cost, years of running with nothing to show. Many people thought it would never succeed. And the difficulty was not only building something that's sensitive, it was that once you have built something that's sensitive, it notices everything. A truck passing on a distant road, waves breaking on a coastline hundreds of kilometers away, a tree falling in a forest, the slow settling of the ground itself. Every one of these shakes the instrument far more violently than any gravitational wave ever could, and every one of them had to be identified, measured, isolated, and filtered out. So the mirrors hang from elaborate cascades of pendulums, isolating them from the shaking of the Earth. The tubes containing the laser beams are among the largest vacuum systems ever constructed, emptier than the space between the planets, because even a few stray molecules of air would ruin everything. The whole thing is a monument to obsessive care, and to the willingness of a large number of people to work for decades on something that might, in the end, detect nothing at all. And there were two of them, deliberately, thousands of kilometers apart, for a simple and clever reason. A local disturbance would only affect one. A real ripple in space, crossing the Earth at the speed of light, would pass through both, with a tiny delay between them, and that delay would even tell you roughly which direction it came from. Nothing counted unless both instruments saw it. And then, in September of 2015, both instruments, 3,000 kilometers apart, registered the same tiny shudder, 7 milliseconds apart, exactly the delay you would expect from a ripple traveling at the speed of light across the width of a continent. And the shape of that signal, when they looked at it, was unmistakable. A rising tone sweeping up in pitch and growing louder over about 1/5 of a second, ending in a sudden peak and then a brief ring, fading away. It was two black holes, each about 30 times the mass of our Sun, spiraling around each other, faster and faster, closer and closer, until they collided and merged into one, circling each other hundreds of times a second in their final moments, moving at a large fraction of the speed of light. And in that final instant, an amount of mass roughly equal to 3 of our suns was converted directly into gravitational waves. For a fraction of a second, that collision radiated more power than all the light from all the stars in the entire visible universe combined. Not more light, it gave off no light at all, pure ripples in the shape of space. And it happened about 1 1/3 billion years ago, before there was anything on Earth more complicated than single cells, and the ripples spread outward through the darkness for 1 1/3 billion years, crossing the void, and arrived here, and gently stretched and squeezed the whole planet and everyone on it, by an amount far too small to notice and passed on. And two instruments, finished just in time, were listening. And here is the detail that makes the whole thing almost unbelievable. The upgraded detectors had only just been switched on. They were not even in their official observing run yet. They were in the final engineering checks, days away from formally beginning, when the signal arrived. A few weeks earlier, and the instruments would have been sitting idle, and the wave would have washed through the Earth and continued on into the dark, and nobody would ever have known. 1.33 billion years of traveling. And it arrived in the same fortnight that we finally became able to hear it, after a century of predicting it and half a century of trying to build something good enough. Some of the scientists on duty assumed at first that it must be a test signal, deliberately injected to check whether they were paying attention, because the timing was too good and the signal was too clean and too loud. It took them months of checking before they were willing to announce it. Rest there a moment and feel how narrow that was. If you find yourself lying awake, sometimes feeling that you have arrived at an ordinary moment in history, consider that a ripple which left its source before there were animals on this planet arrived here in the exact week we became capable of noticing it. Rest there a moment, because that is one of the most extraordinary things our species has ever done. We built a machine so sensitive that it could detect a collision of two dark objects 1 billion light-years away, from the faint trembling it made in the shape of space, and we finished it in time to catch one. And it was the first direct detection of black holes ever. Not their effect on a star, not the glow of gas around them. The objects themselves colliding felt directly here on Earth. We had, in a real sense, learned to hear the universe rather than only to look at it. And the very first thing we heard was two black holes falling into each other in the dark. And then, 4 years later, came the picture. The problem with photographing a black hole is that even the largest of them are, at the distances involved, absurdly small in our sky. To see the shadow of one, you would need a telescope with a dish the size of the planet, which is not a thing that can be built, but there is a trick. If you take several telescopes spread far apart and have them all observe the same object at exactly the same moment and record the incoming waves with exquisitely precise timing, you can afterward combine all that data mathematically, and the result behaves in terms of sharpness, like a single telescope as wide as the distance between them. So a collaboration of hundreds of scientists linked radio telescopes across the whole Earth, from Hawaii to Spain to Chile to the South Pole, and pointed them all at the same target on the same few nights, and recorded such an enormous quantity of data that it could not be sent over the internet, and had to be flown physically on hard drives, including some that had to wait months for the Antarctic winter to end before a plane could collect them. Then it took 2 years to process, and that processing was its own kind of care, because a result like this can go wrong in a very particular way. When you combine data from telescopes scattered around a planet, you do not simply get a picture. You get an enormous quantity of numbers, and you have to reconstruct from them what image would have produced those numbers. And there is always more than one possible answer. Which means that if the people doing the reconstructing are hoping to see a ring, there is a real danger that they will find a way, without ever intending to produce one. So they did something admirable. They split into 4 separate teams, working in isolation, forbidden to compare notes using different methods and different assumptions, each trying to build the image independently. For months, none of them knew what the others were finding. And only when all 4 were finished did they come together in one room and reveal their results at the same moment. All 4 had produced a ring of the same size in the same place with a dark center. 4 independent groups working blind, arriving at the same picture. That is why the result was believed. And in April of 2019, they showed the world the result. A fuzzy orange ring with a dark hole in the middle, not much to look at if you did not know, and one of the most astonishing images ever produced. What you are seeing is the glowing gas swirling around a black hole at the center of a galaxy some 55 million light-years away, an object about 6.5 billion times the mass of our Sun. The bright ring is light from that gas, some of it coming from behind the black hole. Its path bent right around by the extreme curvature of space, so that it reaches us anyway. And the dark circle in the middle is the shadow, the place where the light stops, the event horizon, or as near to it as anything can show. Consider the scale of the thing in that photograph. 6.5 billion suns. Its horizon is larger than our entire solar system, larger than the orbit of the outermost planet, so vast that light, which crosses from our sun to the Earth in about 8 minutes, would take more than a day simply to travel across it. If you were to place that object where our sun is, everything we have ever built or visited or seen up close would be inside it. And notice something about the ring itself. It is brighter on one side. That is not a flaw in the image. That side of the swirling gas is moving toward us, and matter moving toward you at a large fraction of the speed of light appears brighter, exactly as the theory predicts. So even in that first blurry orange donut, the physics of a century earlier was quietly confirming itself in the lopsidedness of the glow. That dark patch in the middle of that photograph is a region of the universe that is not there anymore, in any sense that matters to us. And we photographed it. 3 years later, the same collaboration released an image of the one at the center of our own galaxy, the 4 million solar mass object those patient astronomers had spent 25 years circling in on. Harder to image because it is smaller and changes faster, but there it was, a ring and a shadow at the heart of the Milky Way. Rest there a moment and let the whole arc of it settle on you, because we have arrived at the end of a very long road. 240 years or so, from a clergyman in a country parish, wondering whether a star could be too heavy for its own light to leave, to a photograph, from pen and paper to a planet-sized telescope, from an idea that the greatest physicists of their age rejected as too absurd to be real, to an orange ring on the front page of every newspaper in the world. And notice how the story went. Almost every step of it was taken by people who were told, or who told themselves, that the thing could not be done or could not be true. The idea was forgotten for a century. The mathematics was dismissed as an artifact. The young man who calculated the limit was ridiculed in public. The founding paper appeared in the week. The world went to war and sat unread for 20 years. The waves were predicted by someone who was certain they could never be detected. The photograph required a telescope larger than any telescope could be. And all of it happened anyway, slowly. Sometimes across generations with the person who began a thing long dead before it was finished. But it happened because people kept going back to look, kept following the mathematics where it went, kept building the impossible instrument and pointing it at the sky. That is what I would like you to take from these 3 nights, if you take anything at all before you sleep. Not the darkness of these objects, the patience of the people who found them. And so let it rest now, all of it. Let the whole long story lie down and be at peace. Let the country clergyman rest with his invisible stars and his quiet parish. Let the man who died at the front rest, never knowing what his few lines of mathematics contained. Let the young man on the ship rest, vindicated at last, half a century late. Let all of them rest, the ones who were dismissed and the ones who did the dismissing. The ones who watched the same speck of sky for 25 years. The ones who built a machine to feel a tremor 1 billion light years away. The ones who flew hard drives out of Antarctica so that we could all see a photograph of a shadow. They gave us a universe far stranger and far more magnificent than the one they were handed, and nearly all of them have gone quietly on now, having passed the puzzle along as we all do to the ones who come after. And out there right now, while you rest, all of it is still happening. The great dark thing at the heart of our galaxy is turning slowly, 26,000 light-years away, with its handful of bright stars swinging around it in their long ellipses, one of them coming in close about once every 16 years, as it has for millions of years and will for millions more. Somewhere out in the dark, 2 black holes are spiraling toward each other, and in 100 million years they will meet and send a ripple out across the universe that may wash over this world long after everything we know is gone. And everywhere, in every direction, out to the very edge of what we can see, the faintest possible glow is trickling off horizons that will take a number beyond imagining to fade. None of it needs you. That is the gift of it at the end of a long day. It has all been going on for 13 billion years without your attention, and it will go on tonight while you sleep. and it will still be going on when you wake, and it asks nothing of you at all. So let your breathing slow one last time, and let the amber and the equations and the great blue star in the swan and the orange ring and all of it grow soft and dim and very far away. The story is told. The mystery is not solved, not entirely, and never will be, and that is one of the loveliest things about it. There's always more of the dark left to look at. Let the whole sky settle now and grow quiet and dim, the way a room dims when someone turns down a lamp. Let the galaxies drift on in their long, slow, turning, unhurried, patient, exactly as they have since long before anything here was alive. Let the stars at the center of our galaxy keep swinging around their invisible partner, one slow ellipse at a time, taking their 16 years to come round again, in no hurry whatsoever. Let the great ring of glowing gas 55 million light-years away keep turning, as it has turned for longer than there have been eyes anywhere to see it. And let all of them, all the patient people who worked this out across 2.5 centuries, rest too. They did a beautiful thing. They looked at the darkest and least promising corner of existence, a place defined by giving nothing back, and they would not leave it alone, and in the end they made it give up a photograph. And then, one by one, they set down their pens and their telescopes and went to their own long rest, having handed it all on. You are here, warm and safe and held, on a small solid world in a quiet corner of an ordinary galaxy, and the ground beneath you is exactly where it has always been, and nothing near you is falling, and nothing near you ever will. There is nothing at the edge of your bed but the floor. There is nothing above your roof tonight but the ordinary sky, turning slowly as it always has, full of light that set out toward you a long time ago and is only now arriving. Sleep now. The sky will look after itself, it always has, and it will still be there, turning slowly and patiently above your roof,